Welcome to The Explainer. Let's jump right in because today we're unpacking what is easily one of the most fascinating concepts in modern tech. We're going to demystify exactly how artificial intelligence can create something out of absolutely nothing. To really grasp the astronomical stakes here, just look at this massive endorsement from Yann LeCun, the chief AI scientist at Meta. He flat out called generative adversarial networks, or GANs, the most interesting idea in the last 10 years in machine learning. Think about that for a second. This wasn't just some minor software patch, it was a total, fundamental paradigm shift. It all really boils down to this one big question, right? How do we actually teach a machine to imagine? Like, how does it just whip up a face or a sweeping landscape that has literally never existed in the real world? Well, the answer doesn't lie in staring at some impenetrable static calculus on a whiteboard. It actually plays out as a really high-stakes game. Section 1. The Generative AI Game. Okay, so before an AI can imagine something brand new, it obviously has to learn what our reality actually looks like. For a long time, engineers tried to do this using what's called explicit density. Basically, they were trying to mathematically define the exact probability distribution of real-world data. They were solving these insanely complex equations just to figure out the literal math of a human face. And you know what? It was incredibly difficult. But GANs, they completely changed the game by switching to implicit density. Instead of trying to solve the exact math, the AI just learns by faking it. It completely skips the impossible formulas and learns the distribution implicitly simply by doing. And that brings us to the core metaphor that makes this whole thing tick. A GAN is actually two completely separate neural networks, locked in a bitter adversarial rivalry. On one side, you have the generator. Think of this guy as a master art forger. He takes a vector of abstract random noise and tries to transform it into fake data, like a convincing image. Then, on the other side, you have the discriminator. This is our expert detective. Its one and only job is to look at images and guess, okay, is this real training data or is this a total fake created by the forger? So let's dive right into this. How do they actually get better? It plays out exactly like a turn-based board game. In step 1, we freeze the forger. We train the detective by showing it a mix of real images and fake images, tweaking its mathematical weights so it gets much sharper at catching those fakes. Then it's turn 2. We freeze the detective and we switch over to train the forger. We backpropagate the errors through the network, which basically forces the forger to adjust its own weights so it can produce a much more convincing fake for the next round. But as you might expect, early on, engineers hit a massive roadblock. It's known as the saturation problem. See, when the forger first starts out, its fakes are just terrible, like laughably bad. The detective catches them instantly, with 100% certainty. And because the detective is so incredibly certain, the mathematical learning curve just flatlines. The gradient hits 0. The forger is getting absolutely no useful feedback on how to improve. So how did they fix it? They brilliantly flipped the math. Instead of trying to minimize the detective's success, they tweaked the objective to force the forger to maximize the detective's failure. That simple little flip generated this massive, steep gradient of feedback right when the forger's images were at their absolute worst, which completely unstuck the entire learning process. Now, at this point, you might be wondering, wait, is the AI actually imagining things, or is it just acting like a super fancy copy machine? Well, we can actually prove it's genuinely creating novel imagery by using the nearest neighbor test. We take a generated fake and mathematically search the entire training database to find its closest structural match. And because the resulting neighbors always have entirely different lighting, entirely different poses, and completely different backgrounds, it proves beyond a shadow of a doubt that the model is genuinely generalizing. It is not just memorizing the data. Section 2, Judging the Fakes. Okay, so the AI is generating original work, but how do we actually score a machine on its artistic ability? Well, unlike a simple pass-or-fail math test in school, generative models have to hit all 3 of these specific targets to be considered a success. First, sample quality. The images absolutely have to look real. Second, diverse samples, meaning it can't just draw the exact same face over and over again. And third, generalization. It has to avoid overfitting to the training data. To try and measure this, researchers initially relied on something called the inception score, which checked for quality and class diversity. But it had a pretty fatal flaw. It could totally be fooled if the AI just memorized one perfect image for each category and only generated that. We call that massive failure mode collapse. So the industry evolved. They upgraded to the Freshet Inception Distance, or FID. FID is way smarter. It extracts the deep mathematical features of the generated fakes and directly compares them to the true, real-world data distribution. This gives us a highly accurate track of both true visual quality and diversity. The big takeaway for you here? Lower FID scores mean better, far more realistic AI. Section 3. Upgrading the architecture. You know, the very first scans were incredibly wobbly. They were highly unstable and extremely prone to just crashing altogether. This huge headache was finally fixed with the introduction of deep convolutional GANs, or DC GANs. Essentially, researchers laid down some strict architectural ground rules to build a solid foundation. They stripped out the old dense layers, brought in spatial convolutional layers, and mandated specific activation functions like LiLiQ. By forcing the AI to understand spatial relationships, they effectively cured those wild oscillations and mode collapses that used to plague the early models. And now, this is where it gets absolutely wild. With the stable DCGAGN, researchers discovered the sheer magic of the latent space. They found out they could actually do semantic vector math. Think about this. If you take the mathematical vector for a generated smiling woman, subtract a neutral woman, and then add a neutral man, the network perfectly outputs a smiling man. It's mind-blowing. It proves the AI isn't just mindlessly shuffling pixels around, it actually understands high-level human concepts like gender, accessories, and facial expressions. And man, once they stabilized that architecture, the progress was absolutely breathtaking. Just look at this explosive timeline. In 2009, generative models could barely spit out a blurry, blocky digit. By 2015, we were getting some low-resolution objects. But then, fast forward to 2018 and 2019, we were suddenly generating super diverse, high-resolution human faces, perfectly photorealistic indoor scenes, and these wildly complex landscapes. All of that in less than a single decade? Section 4. Controlling the output. Of course, progress brings new problems, and here we hit a big one. A brilliant forger that only ever paints random daydreams isn't actually all that useful for us, right? We need to be able to tell it exactly what to draw. Enter the conditional GAN. This framework injects a specific condition, like a class label, directly into the model right alongside the random noise. Think of it like putting a leash on the AI. Now, the detective is trained to penalize the forger, not just if the image looks fake, but also if it fails to match the specific condition we asked for. So we can finally say, hey, generate a number 7, and mathematically force the AI to comply. And this exact logic led to some incredible translation models, like Pix2Pix. Now, Pix2Pix uses strictly paired data, so you give it a crude MS Paint-style line drawing of a shoe, and it mathematically translates that exact structural map into a stunning photorealistic photo of a shoe. It uses a combined adversarial loss to make sure it looks real, and a mathematical penalty called L1 loss to guarantee that every single generated pixel aligns perfectly with your original sketch. But that immediately sets up what is arguably the greatest challenge in image translation, the unpaired data problem. What if we want to turn a photo of a horse into a zebra? We obviously don't have perfectly matching photos of a horse standing in the exact same pose, in the exact same field as a zebra to train the AI with. So what do? Well, CycleGAN solved this beautifully, and it brilliantly illustrates the massive power of unsupervised learning. It actually uses 2 generators and a cycle consistency loss. Basically, it translates the horse into a zebra and then forces a second generator to translate that zebra back into the exact original horse. If the original image is preserved perfectly through that entire round trip, the network guarantees it has successfully swapped the style without destroying the underlying structure. It's genius. Absolutely no perfectly paired photos required. Section 5. The next AI frontier. So, what actually happens when we try to push these generative models to their absolute bleeding-edge mathematical limits? Well, when researchers scaled these models up into massive architectures like Big GAN, things got a little weird. We started seeing phenomena like class leakage, where the AI would accidentally fuse categories together. Famously, it generated a dog ball, which, if you haven't seen it, is a mildly terrifying hybrid of a dog's face and a fuzzy yellow tennis ball. To fix bizarre anomalies like that and get consistently high-quality images, engineers had to rely on the truncation trick. Basically, they had to intentionally sacrifice the overall diversity of the images to artificially boost the quality. And that brings us perfectly to the generative learning trilemma. It's a classic pick 2 scenario. You want fast generation, high quality, and high diversity. GANs, they give you super fast sampling and really high quality, but they really struggle with diversity and mode coverage. And this is exactly why the entire machine learning industry is currently pivoting so hard toward denoising diffusion models. Diffusion models, which learn by slowly, painstakingly reversing pure static noise, offer incredible quality and excellent diversity. The trade-off is they are much slower to generate the final image. But that quality and diversity is exactly why the AI image generators you are probably using today on your phone or your computer are powered by diffusion, not GANs. So, we want to leave you with this final kind of mind bending thought today. If generative adversarial networks taught machines the intricate, high stakes game of forging reality, and diffusion models taught them how to meticulously restore reality from pure, chaotic static, what entirely unpredictable, stunning new realities is artificial intelligence going to learn to imagine next? Thanks so much for joining us on this explainer, and as always, keep learning.